Hello, everyone. This is the lecture for section 5.2, the definite integral. So in section 5.1, we sort of defined the construction of the integral, what it's really going to be used for. It's going to be used to find the area under a curve, right? So this section concentrates with now sort of using the definite integral, clearing up a couple things within its definition, and then sort of producing a couple more sort of basic ideas behind the definite integral, okay? One thing I would want everybody to really think about right now, or just get into the habit of doing, is we are talking about areas, right? So a lot of this stuff, a lot of the material that's in section or in chapter 5, sort of refer to it as an area. Okay, I think that'll make a lot of the thinking and a lot of the intuition come much easier to everybody. Okay, so first thing I want to do is go back and define how we define sort of the integral itself, right? The definite integral. Okay, and the equation for the definite integral is this right here. So I'm going to go ahead and dissect this and go through the theory one more time really quick, right? So let's say we wanted the area from an A to a B. So let's say this is my A and this is my B under a curve. Make this a blue curve, right? Let's say I wanted under that curve right there, right? So I wanted this area right here. All of this basically, right? This was the area that I want. Okay, so all of this is what we consider, right, the integral from A to B of f of x dx, right? And the way we did this, right, was, if you guys remember, right, we had an xi minus 1 and an xi. We were taking basically rectangular chunks like this, right? And it was defined by a point. I'm going to go ahead and call it, I'm going to call it xi star, right? The height of this box was f of xi star, right? Given some width of the box, this is what we're going to call dx, right? So the idea was, in order to find the integral, right, in order to find the area of the curve, we draw a bunch of these little boxes. Let me actually make it. We draw a bunch of these little boxes right here, right? A bunch of these little boxes, okay? And we grab those boxes, right? We do multiple of them under the curve, right? And then we just add them up, right? That was this idea right here, right? And from the last section, we realized that there was a bunch of like overestimation, underestimation, right? Depending on which end we use, either the left end or the right end. We fixed it a little bit by just denoting an f of xi star, right? Where it could be any representative value. That sort of answered a little bit, right? But what really did it, what really got us a much more accurate number for the integral, right, was that we grabbed these widths and just started to like make them smaller and smaller, right? We sort of scrunched them together so that the boxes became much more skinnier and skinnier and skinnier, right? They still had a width, but they just were skinny, 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 skinny. And the idea is, if we made those boxes really skinny, right, then there's going to be much less of an over approximation or under approximation, right? And the idea behind that was we were basically using a limit, right? So that's where this thing came from. That's where that limit came from. Okay. So that's the basic theory behind how an integral is constructed, right? Now, what I want to do, right, is now start to introduce this sort of notation right here, the one with the squiggle on it, okay? So the f of x, the thing inside, right? The f of x, That's what we call the integrand, right? The dx, that denotes the variable of integration. You're going to get, we're going to get into the habit of writing dx in this class because it'll become really important once you hit Calc 3, where you're going to have to do multiple variables of integration, where you're going to have to deal with multiple variables of integration. So you're going to have a dx, a dy, dz, a dt, a d phi, okay? So it's going to be real crucial for us to just get into the habit right now of writing in dx, okay? And then the last thing is the a and the b. That's basically the limits of integration. It tells us from where to where we want our area, okay? So now notice what I did here, a difference from section 5.1 to now, right? We do not have the restriction that f of x be non-negative or continuous, okay? So this is gonna produce a problem, and I'll get into it in one of the examples, okay? One thing I wanna go ahead and mention for now is f of x is continuous. If you have an f of x that is continuous, then your f of x is also integrable. That means that this integral from a to b, f of x dx, what happened? It crashed, but thankfully I got it open again. F of x dx, right, exists. Okay, that's what this means, okay? So now, what I want to do is I want everybody to try out this quick check, okay? It's basically 2 for everybody, okay? If you're odd, you're going to be doing the very first one. If you're even, go ahead and do the second one. And I want everybody to try out the last one, okay? Now, in the directions that I'm giving you here, right? I want you all to use geometric arguments for the area, okay? So what I'm giving you here is areas of circles, areas of triangles, okay? Make sure you use those. I haven't shown you how to take the integrals yet, so you shouldn't be able to do this using calculus yet. I just want you guys to use geometric arguments, okay? If you need to graph them, go ahead, okay? So from the quick checks above, what you guys are going to notice is that a problem shows up, okay? For both the odds and then evens, I gave you guys sort of a semicircle. You guys are going to get an area. I'm pretty sure you guys both call them positive areas, right? And then when you guys did the one that everyone had to do, the one with the 2 triangles, right? Some of you guys might have gotten different answers, okay? And that's to be expected, actually, okay? There is a problem here, okay? Because of the definition of the integral, okay? We have to sort of keep in mind what kind of integral we're messing with, right? Is it going to be a positive? Is it going to be negative? Okay. Because of the definition of how we defined the Riemannian sums, how we did the limit as n approaches infinity of the summation of that, right? Okay. So we have to introduce 2 more definitions here, okay? The first one is of a net signed area, okay? And the net signed area is this right here, okay? And if, let's go back up here, let's say A1 is the area of f of x above the x-axis, and A2 is the area below the x-axis, okay? Then we have this situation. It's going to be A1 minus A2, okay? The total area, right, is defined by this right here, A1 plus A2, okay? So I know this sounds really, really weird, okay? But like I said, a lot of this stuff from calculus, so long as you sort of understand the picture that goes along with it, you understand sort of like the idea or the definition behind it. So I like pictures. Let's go ahead and do pictures of these. So let's say we had the net signed area, right? So the net signed area, and actually, I need to make this before I forget again. Okay. So let's say we had a function that did this, right? And I'm going to use my blue again. Right? So, and let's say I wanted this area from this A to this B. Okay. So I want all of this. I want all of this area right here. Try to make this as nice as possible. Okay. I want all of this area right here. Okay. The net signed area actually will do this. Okay. That area is going to be my A1, correct? And this right here is going to be my A2. Okay. What the net signed area is going to do is it's going to consider this area right over here, right? The area that's below the x-axis. It's going to consider it as negative, right? So what ends up happening, right? If we take a look at A1 minus A2, right? Is that A2, since it's negative, takes away area from A1. So it sort of compensates, right? For the fact that A2 is actually negative area. Okay. The total area does the opposite. So the total area, I'm going to try to draw the same thing, right? Draw the same thing. So squiggle, little dip. There we go. Okay. And I want my same area from A to B. It's still this, right? Whoa, there we go. Still this right there, right? This is still A1. This is still A2, right? But now, notice I drew them both in green. A1 plus A2 is the combined total area, right? I'm going to put no takeaway, right? Is the combined total takeaway. Oh, sorry, but it's the combined total area, no takeaway. So in this case, what happens is basically A2, we consider it as a positive area, even though it is going to be defined by our rules and definitions of the definite integral from above, right? This is considered a negative area. But since we're talking about the total area, we are just going to need to know to turn it positive. Okay. It'll take some time to get used to, right? This is one of the very few times where you can go ahead and say, oh, I'm looking at this thing. I'm just going to change it positive because I need it to be positive. Okay. That's basically it. Okay. So that's the difference between signed area and net area. It's going to be really crucial when we get a little further in the course and when you get into Calc 2. Okay. So what I want to do now is let me go ahead and do out the example that I gave you guys as a quick check. Okay. So let's say we wanted to find the net signed area, right, and the total area. So let's do the net signed area first, right? So the first thing that we're going to need, right, is this. I'm going to go ahead and, like I said, I'm going to be using, because I haven't shown you guys how to do this yet. I'm going to be doing geometric arguments, right? So the area of a triangle, right, is 1/2 base times its height. Okay, that's one of the equations that we're going to need. Okay, so let's do first the net signed area first, right? So then this means that it's going to be the integral from -6 to 6 of 2/3x dx. Okay, so that area is going to be this area right here. Let me highlight the stuff that I'm going to be talking about. This area right here, plus this area over here. All of this, right? So let's go ahead and label some of this stuff, right? This is going to be, and I need to do it in red, right? A1, and this is going to be my A2, right? So the area of each one of these, let me go ahead and calculate them over here. The area for this bit, right, is the 1/2 times the base. So it's going to be 6 times the height, which is going to be 4. Right? So that's going to be equal to 1/2 times 24, which is equal to 12. So what I have here, right, is going to be still an A1 plus an A2, right? However, A1 is negative. So this is where I'm going to do -12 plus 12. This is going to be equal to 0. Okay. So now let's go ahead and do the total area. The total area, right? -6 to 6 of 2/3x dx. It's still going to be an A1 plus an A2. It's still going to be the two areas that we want, right? However, now that I'm talking about the total area, this first one, my A1, before it was negative. Now I get to turn it positive. Why? Because I need it to be positive because I'm doing the total area. You see how I'm doing that? So then therefore, this is going to now be 12 plus 12 is 24. So this is the thing that you guys probably were sort of tripping out on when you guys were doing the quick checks. Which one is it? Is it 0 or is it 24? The answer is it's both, right? It depends on which one you're looking at. It depends on which one you're looking at. Okay. So when you do when you're doing the assignments for this section, solely use geometric arguments. Okay, I haven't shown you guys how to take integrals yet. You might know how to. Actually, some of the rules have been provided in section 410, and I believe some in 5.1 as well. But you're not required to use them if you don't want to. Like I said, it is much more to your benefit just to use the geometric arguments. Okay. Okay. What I want to go through now is a couple of properties of the definite integral. Okay. Like I said, we are expressing these things, right? These mathematical terms as areas under a curve. Areas under a curve. So if you keep the idea of areas under a curve, right, then these definitions and these properties should make a little bit more sense. Okay, so I'm going, like I said, I like the pictures for them, right? So I'm going to do the picture for each one of these properties. The property is going to be on the left. The picture is going to be on the right. Okay. So the first one, the limit, or sorry, the integral from a to a of f of x dx is equal to 0. So that basically says, suppose you had a function, right? And your limits of integration went from a to a, right? Then there is no area here, right? So then therefore, right, the integral of f of x dx, whoops, from a to a should be equal to 0. There's no area. There's no area there. It's just a straight line, right? Okay. Okay. Next one. It's sort of this takes care of the order of the limits of operation, or the limits of integration. Okay. Suppose we wanted to do the integral from a to b of f of x, right? And here's my f of x, right? So I'm looking for this area right here, all of this, okay? This is what we're looking for, okay? If we want to find that area, right? Notice that the limits of integration go in this direction from a to b, right? This is equivalent, same function, right? And I'm going to do from a to b again. Do from here to here, all of this same area in pink right here, right? If we go in the opposite direction, right, then we have to take the negative up. So basically, if you go from A to B in the forward direction, right, that is equal to the negative area in the opposite direction. That's it. Okay. Okay. The next one, f of the integral from A to B of f of x plus g of x is equal to each one separate. Okay, so hopefully this one already makes sense. So suppose, right, suppose you had, you know, a big, huge function up here, right? From A to B, whoops. And you wanted this area, right? You wanted all of this. Just all of it. You wanted this whole entire area, right? So this was, this right here is f of x plus g of x, right? Then this is equivalent to both of them put separated out. So let's say it was a g of x, right? And an f of x, right? From A to B. It's both of these areas put together. So it's supposed to be this area, the big one from f of x, right? Plus the area of g of x, this little bit right here, right? You basically get to add both of them together, right? The addition of both of them together should get you the original one, this one right here. Okay. The second one, the one right below it, sort of works the same way. So let's say, right? This is f of x and this is g of x, right? And you wanted to find from A to B, you wanted to find this area right here, right? You wanted this little strip right in between the two. Right? Then that is equivalent to, I'm going to try to draw it all over again. That's f of x. This is g of x. We still want the area from A to B. Okay. That's equivalent to finding the area of f of x, this big one right here, right? All the way down, right? All the way down to the bottom, and then taking away the area from below it. That's simple. You see that? Okay, like I said, think of these as areas, right? Okay. Suppose you had a c times f of x. So let's say this is my, whoa, make it a little longer, yeah? So suppose that this is my c times f of x, right? And same idea, right? A to B. I want this area right here. I want all of this. Oh, there we go. I want all of this. Okay. Then that is equivalent to, let's just say this is f of x, just good old regular f of x, right? That is equivalent to me doing from A to B here, right? Finding the area between A and B. So finding all of this. It's equivalent to finding all of that area, right? And then grabbing all of that and then just do times C. That's it. Multiply it by C. Okay, like I said, areas. These are areas. So you can multiply areas. You can add areas together. You can take them away. They still work the same way. We're just introducing calculus notation for it. Okay. Okay. This one's going to be particularly useful much later in Calc 2, okay? That for any constant value, right? C between A and B, right? The integral from A to B can be basically cut up into that intermediary point C. Now, the statement itself is for any point, okay? It doesn't even have to be inside A to B, but it's best seen if I do it somewhere in between, okay? So let me show you guys what I mean. So let's say I wanted to take this area right here, right? So this right here is the integral from A to B of f of x dx, right? Then I can choose any intermediary point, C. Like I said, it doesn't have to be inside A to B, right? But it makes most sense when I draw it between A and B. So if this is A and this is B, I'm going to choose my intermediary point. It doesn't really matter where. I'm going to choose that to be C right there, right? So then that is equivalent to, let me draw my functions again. Here's my f of x, wrong color. Whoa. I'm trying to draw them sort of equal. There we go. Okay. I want this area, right? Come on, where are you? Whoa. I'm drawn on a tablet, so it's really hard to, there we go. There we go. All right. So this is equivalent to finding the area from here to here, right? And then adding on the area that comes after it. You guys see what that means there, right? Like I said, pictures make more sense, right? So this is going to be the integral from A to a C of f of x, right, dx. And then this right here is going to be the integral from C to B of f of x dx. Right? So this idea, right, this property says that I can basically split it wherever I want, right? With a value C, and then add the two values and add the two integrals, the two areas together afterwards. That's simple. Okay. Okay, these are theorems that show up in the book. Okay, which is these are like I said, once you start realizing that we're playing around with areas, right? These make sense, right? So if f of x is bigger than 0, so let's say f of x is this, right? And this is always going to be bigger than or equal to 0, right? Then you're guaranteed that the area for it, right? So same figure, the area between A and B, I forgot to do my A and B here. This area right here has got to be positive. I know this is a sort of like a like a no-brainer, right? But it needs to be stated. Okay. Next one. If f is always bigger than g over ab, then the integrals must be bigger themselves too. Okay. So again, a no duh, right? So let's say you had an f of x, right? This is f of x. And here's your g of x, right? Over an interval ab. So here's a and here's b, right? Then the integrals of both. So that means if I draw the squiggle here and I do a to b here, right? This area right here, right, has got to be bigger than this area right here. Gotta be bigger. That's all this is saying, right? So then this right here is the integral from a to b of f of x dx, right? And this is the integral of a to b of g of x dx. This is all this is saying is that this one has got to be bigger than this. That's it. That's simple. Okay. Whoa. Erase too much there. Okay. And I think the last one that I want to cover here, right, has to do with basically a lower bound and an upper bound to this area. So let's say you had a function f of x, right? I'm going to do something like this. Okay. And I wanted my area from a to b, right? So here's a to b. So I want this area right here. This one I have to take a little bit more care in drawing. Let's say you want this area right here, right? All of this is what you're looking for. Okay. All of this is what you're looking for. So this little bit right here is, I'm going to write it over here. This is the integral from a to b of f of x dx. Let's say we're looking at that thing, right? And suppose, right, that's what this statement's going to say right here. So this statement right here, come on. Is it? Come on. Oh my. Okay. My OneNote has decided to give up on me. Give it a second. I'll cut here and come back in a second once this is all done. Okay, we're back. My OneNote works again. Okay, so let me get back to this one. Okay, suppose we are looking for the integral, or we're going to analyze another property of the integral from a to b of f of x dx. So we're looking at this thing, right? That's the thing in the pink that's on the right hand side there. Okay. Now, suppose you have a function f of x, right? Suppose you had two values, a little m and a big M, right? That sort of bound your function above and below. Okay, what do I mean by that? Suppose that you had a little m value, so a little m value down here, so this is little m, right? And suppose you had a big M up here, right? So notice that my function f of x sort of exists between both of these two values, the little m and the big M, right? And what I'm going to do is I'm going to connect A and B all the way up. There we go. There we go. Right? Okay. So now I want everybody to notice this. There is now two boxes, right? There's this box down here. This box down here. Okay. And then there's a big box that goes all the way up and over. Right? You guys see that whole thing? Okay. The area for this little box right here, right, is going to be M times B minus A. Okay. So this is equal to area of the little box, right? And then this up here has the same idea, right? M times B minus A, area of the big box. Okay. What this property is saying, right, is this, that if I want the area in the pink, this area right here, right, then it's got to be bigger than the area of the small box, right? And smaller than the area of the big box. That simple. Okay, so let me refresh this a little bit, really. Okay, let's say you have a function f of x, right? And I never wrote in f of x here. So this is f of x right there, right? And I want the area between a and b of f of x, right? So I want the integral from a to b of f of x dx. And suppose that my function is bounded above and below by a little m and a big M, right? Then the area under my curve f of x has to be bigger than the area of the small box. So this one right here, right? And it's got to be smaller than the area of the big box. Okay. So like I said, if you picture these as areas, the theory, the idea, the definitions, these properties make much more sense. Okay. I believe that is it for this section. Next up is lecture questions. If you have any questions, I'll be in my office hours today, in my Zoom room today, from 3 to 6 p.m. At in the lab and in my Zoom room. Okay. Otherwise, you can send me an email. I know I'm behind on my emails. Please bear with me. I'll be answering those a little later on today. Okay. Study hard, and I'll see you guys around.